Hi, my name is Yasin Mikhailov and welcome to our short video series on pulse measurements with a vector network analyzer. We have discussed so far average pulse measurements and point-in-pulse measurements. However, there is one more topic that we need to cover, and that is pulse profile measurements. If we would like to look at the pulse in its time domain or if we're interested in parameters such as pulse troop, overshoot, ringing, rise time, we will need to use the pulse profile measurement option. And I have a very special guest with me here today, Jamie Lunn, who will tell you more about the pulse profile measurements. Jamie?
Thank you very much, Yasin. So we saw in the last video that when we're looking at point-in-pulse, effectively there is a limitation where it takes some time to download the data between each pulses. So this pulse profile mode, the K7, effectively overcomes that. So what we're doing here is we're streaming the data out directly from the digitizers at their full rate, which at 125 megahertz gives us a resolution of 8 nanoseconds. So if we look here on the slide, then we see a repetitive pulse train here, and with the widest measurement bandwidth of say 30 megahertz, we learned that it takes 32 nanoseconds to complete the data acquisition. So what we can do is if we interleave numerous measurements on top of one another, then what we can do from that is extract out a much finer resolution than would ordinarily be available by just sampling one data point. So here, if we illustrate this by data point 1 being triggered at the start of the first RF pulse, then the second data point gets triggered here on the second RF pulse. And there's an 8 nanosecond spacing between the two. And then the third data point on the third RF pulse, and so on. And so what we see here then is a time resolution of 8 nanoseconds between the start of each of the measurements, but a total sampling time of 32 nanoseconds to complete the acquisition for each of the data points. So what this effectively gives us is a rolling average over the pulsed measurement that we're trying to make. And remember here, the key thing is that our network analyzer is a complex measurement instrument, so it's collecting both the magnitude and the phase information. So as we look at the real pulse, we see the first data point here, then 8 nanoseconds later, we start the sampling process for the second data point, third data point, and so on, until we start to reconstruct the whole shape of the RF pulse, but shifted by this 32 nanoseconds. So the key thing here is that we can measure any pulses that might be present. So it doesn't have to be a continuous pulse stream. It could be a single shot pulse. We get very fast resolution of 8 nanoseconds to really identify what's going on with that pulse, to see if there's any kind of overshoot, undershoot, see the rise and fall time, and more importantly, see if there's a slope both in the magnitude and the phase. And unlike the average pulse measurement that we looked at, there's no loss of accuracy due to the pulse desensitization, because we're actually making the measurement during that time when the pulse is present.
So Jamie, it seems to me there's quite a few benefits to the pulse profile option if you're trying to look in the time domain of the pulse. What about setting up the measurement? Is it complicated?
Again, like what we showed with the pulse profile, we have a nice intuitive user interface that kind of does all the hard work for you. So let's go back to the network analyzer and see how that gets set up. Okay, so here we see the setup left over from the last video for point-in-pulse. If we just go back into the pulse mod dialog, we can see that we've got the same settings for pulse width, 10 microseconds, pulse period 100 microseconds, so 10% duty cycle. We have a pull down menu here which selects the sweep type that we're currently using. So before this would be say linear frequency or power sweep. Down the bottom we have a dedicated sweep mode for pulse profile, the K7 mode. And in the timing diagram, remember this is a valuable feedback in this window to show us really what's happening from the waveforms, both for the pulse modulators, and if we're using any external pulse generators to synchronize with our hardware, we can see that we have our 10 microsecond pulse and then a window of 20 microseconds. So let's see how that looks. I'm going to use the auto set button again to optimize everything, and then click OK. Let's pop a marker on here so we can see at the moment we've got output power of 10 dBm, and then we can see the off time of the pulse. We can just add some averaging onto this to give us a much better on-off ratio, or to view the on-off ratio, I should say.
I think you should mention a few words about this, because this is a very, I think, special feature that we have.
Yes.
Complex averaging.
Yes, so essentially what happens here is if we're looking at the complex data, then if we perform the averaging function in the complex domain first, before then displaying the magnitude or the phase, we're effectively getting a subtraction of the noise. So it gives us a much lower noise floor of the measurement without having to use a lower measurement bandwidth. So if we just, with my marker, I'm just going to set a delta marker, and we can just pop that over to here. So we can see about 100 dB of on-off ratio is visible there. I'm going to just pop back into my pulse measurement dialog, because what I want to do now is look at a larger number of pulses, and then we can extend the time window of what we're viewing the measurement over. So we have a pulse period of 100 microseconds. Let's set this to 500 microseconds, say, just so we can see a number of pulses here. And again, we see in the timing diagram how this will look. Click OK. And I think here it's pretty obvious that we're starting to lose resolution a little bit, because what I didn't do is change the number of points. So we can add a much larger number of points here, say 10,001, but this will not change the sweep time, because the ADCs here are always running at their fastest rate. So the sweep time on the display is no longer defined by the number of display points. It's simply just taking the fastest measurement possible. So for 10,001 points, we can see it's still updating extremely fast. Now, the nice thing I can do with the user interface is we can zoom in around relevant pulses like so, and then take a closer look at what's going on here, maybe to place some markers in the relevant areas on the pulse, maybe to move the marker around on here to wherever we want on the pulse. We can then move to, say, the next RF pulse here, and then do something similar, add another marker onto this one, and so on. So you can then, over a larger number of pulses, start to get a feeling for if there's any difference from pulse to pulse variation, both in terms of the magnitude, which we're seeing here, and if we want to see the phase, then we can go into the format menu and simply change this to phase, and then satisfy ourselves that there's no phase droop over the pulse as our amplifier is heating up during that pulse period.
So thank you, Jamie. This actually, I find this particular feature quite useful. And in conclusion, could you just say a few words about measurement accuracy, recalibration? Is it possible?
Yeah, sure. So when we're using our network analyzer to perform measurements under pulse conditions in this way, we're essentially doing the same thing as we would have done with normal S parameter measurements and normal power measurements. So we use a USB power sensor to calibrate the absolute accuracy of our receivers. So in effect, transferring the accuracy of the power sensor to the highly linear receivers within the ZNA network analyzer.
Thank you, Jamie. So you saw how easy and straightforward it was to set up such a complicated measurement as pulse profile. Just to recap, we have 8 nanoseconds of resolution time, we have 100 dB on-off ratio, fast measurement time, and last but not least, very good accuracy, excellent accuracy. Thank you for watching this video series, and see you next time.